Hello everyone, welcome to my channel. In this lecture, we will discuss about the production of maleic anhydride from the partial oxidation of benzene. There are two ways by which we can prepare maleic anhydride. The first method is the preparation of maleic anhydride from the partial oxidation of normal butane. And the second method is the preparation of maleic anhydride from the partial oxidation of benzene. The benzene method for the production of maleic anhydride is old method, and nowadays it is converted to the normal butane method. Normal butane, the maleic anhydride which we prepare with the help of normal butane oxidation is environmental friendly method, and as we know benzene is carcinogenic. So nowadays most industry converted uh, from the old method, which is the partial oxidation of benzene, to the new method, which is the partial oxidation of normal butane, to produce the maleic anhydride on large scale. So, in this lecture, we will discuss the old method, which is the production of maleic anhydride from the partial oxidation of benzene. And this method is not very economical as compared to the normal butane method. The normal butane method is efficient, environmental friendly, and it produces large amount of benzene. A large amount of maleic anhydride can be prepared from the normal butane oxidation process. But some industry still use the benzene to prepare the maleic anhydride. So we will discuss the preparation of maleic anhydride from the partial oxidation of benzene with the help of Aspen HYSYS. So first of all, we will open the Aspen HYSYS and we will go to the component list. This is the component list. Click on add to add the component. So there are many components. The first component is benzene, and second is oxygen, nitrogen, carbon monoxide, carbon dioxide, water. So benzene, oxygen, nitrogen, water, carbon dioxide, carbon monoxide, ethane, propane, and maleic anhydride. Maleic anhydride. Maleic anhydride. This is the molecular formula of maleic anhydride, C4H2O3. It is organic compound and it belongs to the hydride family. So its formula is C4H2O3, maleic anhydride. Its boiling point is about 210, about 200 degrees centigrade, and at room temperature it is liquid. It can be also solidified. So this is the maleic anhydride. Maleic anhydride. This is our main product, and the first is the dibutyl phthalate. Dibutyl phthalate C16H22O4. This is dibutyl phthalate. It is the solvent or absorbent. It is using in the absorption column to remove or recover the maleic anhydride from the waste gases. So it is absorbent. It is absorbent or solvent. So dibutyl phthalate. Dibutyl phthalate. Okay. So these are our component: benzene, oxygen, nitrogen, water, carbon dioxide, ethane, propane. Okay. Now we will go to the fluid package. So you can use the NRTL, non-random to liquid package for ideal cases, or you can use Antony. I am using the Antony equation of state. This is the T minimum, T maximum, coefficient A, B, C, D, E, etc. Okay. Now we will go to the simulation and we will make a process flow diagram for the preparation of maleic anhydride. So there are various equipment which are using for the preparation of maleic anhydride in industries. So first of all, this is a pump, this is compressor, pump, compressor, and the third one is the uh, heater. This is a mixer, part heater, and egg bait plug flow reactor. But remember, we will add catalyst to the plug flow reactor. It will become the peg bed reactor. The dimension and all the characteristic of catalyst will define later. This is the peg bed plug flow reactor that will convert it into the peg bed reactor later. Okay. This is cooler. You can also use heat exchanger, but I am using cooler. Absorption column. Go to separator. Select absorption column. Drag and drop the absorption column. Now go to the separator and drag and drop the distillation column. Okay. Now close this one. Model fillet window. Okay. Okay, so this is, we will rename each equipment. This is pump. Let's rename it pump. Inlet to the pump is benzene is entering. This is the favor benzene which is entering. So as we know that maleic anhydride is produced from the partial oxidation of benzene. So benzene will react with oxygen and it will produce the maleic anhydride, carbon dioxide and water. The reaction for the maleic anhydride production is present in literature in various research paper. You can just Google it. So the main reaction is the reaction between benzene and oxygen to produce maleic anhydride. So for that purpose, we will first of all we will pump benzene. We will increase its pressure. So we will take pure benzene. So this is benzene, the inlet, and it will pass through a pump to increase its pressure. After that, we will heat it the benzene to increase its temperature. Because the reaction between benzene and oxygen to produce maleic anhydride is in gaseous phase and it is exothermic reaction. So this is pure benzene. Okay, the outlet is suppose stream number 1 and the pump energy is PE, pump energy. You can use pump energy or pump work, etc. So close this one. Now this is stream number 2. Let's delete this one. Okay. Now this is a compressor. Double click on it. This is compressor. So compressor, and this is stream air. So air oxygen will enter, and the compressor energy is CE. And this is stream number 2. Let's check it. This is stream number. Suppose this is stream number 2. Okay. Stream number 2. Okay. This is the pure benzene. The pump will increase its pressure, and the pure benzene is it. Let's double click on the benzene stream. The pure benzene is at 30 degree centigrade and 1 atmospheric pressure, and its molar flow rate is, sometimes its pressure is very high, so I am assuming 1 atm, and the molar flow rate of benzene is 50 kilomole per hour, and the composition it shows unknown composition, so it is a pure benzene. Mole fraction of benzene will be 1. Mole fraction of benzene is 1. Okay, so it is passing through a pump. This pump, the pump will increase its pressure. So double click on stream number 1. The pump increases its pressure from 1 atmosphere to 3 atmosphere. Suppose 3 atm. Okay, Now double click on oxygen stream. This is oxygen stream. It is entering to the compressor, and the oxygen is at 30 degrees centigrade, 1 atmospheric pressure. I'm assuming this value. You can put other value according to your problem. So the molar flow rate of oxygen, I'm assuming that the molar flow rate of oxygen is 3500 kilomole per hour. It is an excess air, excess oxygen. So the composition of oxygen is, it is pure oxygen. So oxygen mole fraction is 1. Oxygen mole fraction is 1. Okay. This will pass through the compressor, will increase the pressure and temperature of oxygen. So double click on compressor, and here this is the compressor. So here you can see the compressor efficiency is 75. Okay, it is okay. Now double click on stream number 2. This is the compressor outlet. The compressor outlet, we have no information about compressor outlet temperature, but the compressor will increase the pressure of oxygen from 1 atm to 7 atm. 7 atm. So that the Aspen HYSYS will calculate the temperature of this stream. It is 313.5 degrees centigrade. Now this stream number 1, this is the high pressure benzene will pass through a heater, and to increase its temperature from 30.10 degrees centigrade to 120 degrees centigrade. So this is heater E100. So we will rename it heater, and the inlet to the heater is stream number 1, the pressurized benzene. Okay, and the outlet of the heater is stream number 3. Suppose stream number 3, it shows require energy stream. So require energy stream. So require, double click on stream number 3, and the heater increase the temperature of pressurized benzene to from 30 degree to 120 degree centigrade. I'm assuming 120 degree centigrade. Now pressure, so there is no pressure drop inside the heat exchange, the heater. So double click on heater, and here required energy stream. So energy stream, the heater energy is HE, heater energy. That shows unknown delta P. So go to the parameter, and the pressure drop inside the heater is 0. But in reality there is some pressure drop. I am assuming that there is no pressure drop. Okay, this is heater. Okay, now this is a mixer. So stream number 3 and stream number 2 will mix in a mixer. Stream number 3, pressurized benzene, and the high pressure oxygen will mix in a mixer, and it will produce stream number 4. Stream number 4. Stream number 4. Okay. Okay. So this is stream number 4. Now this stream number 4 will heat it in a fired heater. So double click on this fired heater. Here you can see fuel stream, air stream. So fuel will burn inside the fire heater to increase the temperature of the inlet stream. So inlet, which is what is entering the mixer outlet. Stream number 4 is entering to the heater, fired heater. Stream number 4, and the stream number 5 is coming out from the fired heater, and the fuel, so I'm using the natural gas. The natural gas is burning in the presence of air inside the fired heater to produce the combustion product, a product of combustion, which consists of carbon dioxide, carbon monoxide, and other gases. Okay, now it shows non-zero composition are required, so we should define the air and natural gas stream. So close this one, and here this is the natural gas and air stream. Natural gas and air stream. This is the fired heater, natural gas. Double click on natural gas. The temperature of natural gas is suppose the natural gas temperature is suppose 30 degree. Pressure is 1 atmospheric pressure. The molar flow rate of natural gas. So you can assume the natural gas, suppose 100 kilogram mole per hour, and the natural gas is composed of, suppose I'm assuming that natural gas is composed of ethane and propane only, and major portion of the natural gas is ethane and some minor propane, 3% propane and 97% ethane. Click on OK. Now air, this is air, so double click on air, and the air temperature is, suppose it is 30 degree, 1 atmospheric pressure, but in reality this pressure can be increased 3 or 4 bar, or higher pressure, higher temperature. The molar flow rate of the air, the molar flow rate of the air is, suppose 400, because fuel to air ratio, air to fuel ratio, I am assuming air to fuel ratio of 4:1, so 400 and 100, 400 divided by 100 is equal to 4:1. So okay, and go to the composition of air. Air consists of, as we know, 21% oxygen and 79% nitrogen, but in some cases air consists of 78% nitrogen and the remaining is oxygen. So I'm assuming 79% nitrogen and 21% oxygen. 79% and 21% is oxygen. Okay. Now double click on the fired heater. So it shows missing heater efficiency or flue gas temperature. So if you have information about the flue gas temperature, the temperature of this stream, so you can define, you can solve the fired heater. If you have the information about the efficiency of this fired heater, you can also solve this heater. So I'm assuming we will go to the parameter. I'm assuming that the fire heater efficiency is 80%, suppose, and I'm checking it that whether it is working or not. So 80%, suppose. So it shows that temperature cross try to decrease the fire heater efficiency. So it shows Aspen HYSYS tell us that this higher efficiency, the temperature will cross, the heater will not work at this higher temperature, higher efficiency. You should decrease your efficiency. So I am decreasing it to 70% and check it is not working. So 65%, whether it working or not, again it shows temperature crossing. 64% not working, 60% okay. So 60% is okay. So here you can see the product of combustion temperature is 485.2 degrees centigrade, 1 atmospheric pressure, and 551.6 kilogram mole per hour is the molar flow rate of the combustible of the flue gases. So this is the flue gases molar flow rate, temperature and pressure, etc. So now this is stream number 5. Now we will enter this stream number 5 will enter to a peg bed reactor, to a peg bed, stream number 5. The outlet is stream number 6. Okay, it shows require energy, it require a reaction set. So we have not defined reaction. The main reaction, which is the partial oxidation of benzene to produce maleic anhydride, water and carbon dioxide. So we will go to the property and we will define our reaction. So go to the reaction, click on add reaction. This is a kinetic reaction. Click on add reaction, close this one, double click on reaction number 1, and here the component. So the component of the reaction is benzene react with oxygen and it produces the maleic anhydride, carbon dioxide and water, and this is exothermic reaction. Remember, this is exothermic reaction, and this is the partial oxidation of benzene to produce maleic anhydride, water and carbon dioxide. So this is the main reaction. So the stoichiometric coefficient, so this reaction can be, you can watch this reaction, you can it is present in literature and research paper. So this is the main reaction. The stoichiometric coefficient for this reaction is 1 mole of benzene react with, for reactant the stoichiometric coefficient will be negative, for product it will be the positive. So 1 mole of benzene react with 4.5 mole of oxygen and it will produce 1 mole maleic anhydride, 2 mole carbon dioxide and 2 mole water. And these reactant and product are in gaseous phase. And here the reverse order of the maleic anhydride is 1. So the maleic anhydride is first order, and first order The reaction is first order with respect to maleic anhydride, and it is a gaseous reaction. So we will use the partial pressure, and our base component are the limiting reactant is benzene, and the reaction is taking place in the vapor phase, not in the liquid phase. So vapor phase, and the pressure, you can use the pressure. Suppose I'm using the bar or some other. These are the rate law. This is the rate of reaction. Forward reaction minus the rate constant is a function of forward minus backward reaction. So k the rate constant, and it is the Arrhenius. K is the rate constant. And the rate constant of reaction can be obtained from the Arrhenius equation. This is the Arrhenius equation. Here this is the pre-exponential factor or the frequency factor. E is the activation energy, and activation energy is nothing but it is the minimum energy which are required by molecule to form an intermediate product. And once the intermediate product is formed, the intermediate product then will convert it into the product, which are maleic anhydride, water and carbon dioxide. So, and the TB, the B is 0. I'm assuming the B is 0 in this problem. So A is the pre-exponential factor. Usually the pre-exponential factor value is very, very large. It is a collision factor or pre-exponential factor, but I am using that the pre-exponential value is factor value is 77. E is the activation energy. Its unit is joule per mole or kilojoule per kilomole or joule per kilomole per mole, etc. So the activation energy value in this case is 25,143, 25,143, 25,143 joule per mole, joule per gram mole. Okay, that is solved. Now close this one and attach the reaction to the fluid package, which is the Antoine equation. So we will click on add to the fluid package, attach attach the reaction to the Antoine equation of state. Select attached, it is attached. Now double click on the reaction and see this exothermic reaction. The enthalpy of this reaction is this one, 1 minus 1.8 multiplied by 10 raised to power 6 kilojoule per kilogram mole. Okay, at 25 degrees centigrade. The standard enthalpy of this reaction is calculated by the Aspen HYSYS. So this was the reaction. Now we will go to the configuration, the simulation, and here this is the reactor. Double click on the reactor, and here it should require reaction set. So we will go to the reaction and we will add our reaction. So the reaction set number 1 is added. Now the error show that unknown dimension, that what is the length of your reactor, what is the diameter of your reactor, what is the diameter of the packed bed reactor, what is the length of the packed bed reactor. So we will go to the detail. This is the reaction. Okay, you can view your reaction like this one. This is the main reaction. Okay, now go to the rating, and here volume of reactor, length of reactor. So what is the length of the PBR, the packed bed reactor? So I am usually in literature they are using the value from 5 to 8 meter length. I am assuming 2 meter. Suppose the reactor is 2 meter, and the diameter of the packed bed reactor is suppose 0.1 meter. It shows that unknown. Now this is the pack. If it shows if the wide fraction of the reactor is 1, that means that it is a plug flow reactor. But I am using catalyst, which is vanadium pentoxide. So vanadium pentoxide, and the vanadium pentoxide is supported on the support, which is molebdnium trioxide. So the active site on the catalyst is vanadium pentoxide, and the support phase of the catalyst is the molebdnium trioxide. So usually it is 70%, about 70%. The 30% is the active site and 70% is support. So this is the wide fraction. So the wide fraction can be obtained from the Argon equation, and it is used for the packed bed reactor. So I am using the packed bed reactor, and the wide fraction is nothing but it is the space between the catalyst particle inside the packed bed reactor, and this value can be obtained from the Argon equation. So usually the wide fraction value is in the packed bed reactor are usually 0.4, 0.5. It is given in literature, so I'm assuming 0.5. Okay, now go to the reaction, go to the worksheet. Okay, this is the go to the work reaction and go to the work all. So number of segment is 20. Okay, minimum step. This is okay. The particle diameter. So what is the diameter of the catalyst particle? What is the diameter? So here the diameter is 1 mm, but I'm using the 5 mm. My catalyst particle is 5 millimeter, and my catalyst particle is spherical. So its sphericity is 1. If the catalyst is not spherical, its sphericity will be less than 1. So sphericity can be obtained from the your particle technology book. You can obtain the value about the sphericity. So this is the sphericity is 1, and the density, the solid density of the catalyst is 2500 kilogram per cubic meter. The bulk density of the catalyst is this one, and the solid density. Now the solid density and the bulk density relation can be obtained. You can check the relationship between the solid density and the bulk density relation in the book of the element of chemical reaction engineering by Fogler. You can check the relationship between the bulk density and the solid density of catalyst. So usually the bulk density, this is small, and this solid density is high, and the solid heat capacity, this is the heat capacity of the catalyst particle. So if you have information about the heat capacity of the catalyst particle, mean the Cp value of the catalyst is this one. If you have information, you can put like 300, 400, 500 kilojoule per kilogram and 2 degrees centigrade. Okay. Now it shows the unknown delta P. What is the delta P and your reactor? So we will go to the design, go to the parameter, the delta P value here. You can use your own value. This can be obtained from experiments, and from pressure gauges. You can obtain the pressure drop value and the inlet and at the outlet. So suppose at the inlet, suppose the pressure is 2 bar, and at the outlet the pressure is 1 bar of the reactor. So the delta P will be 1 bar, P2 P1 minus P2, and it can be obtained from gauges, from experiments, etc. Or you can use the organic equation. Suppose if you information about the pressure, you have the diameter of the catalyst, the sphericity, etc., the density, the other parameter of organic equation. So you can easily obtain the pressure drop from organic equation. You can solve the organic equation to get the pressure drop. So I'm assuming that the pressure drop for this reactor, packed bed reactor, is 10 kilopascal. So okay, now close this one. Close this one. This is the packed bed reactor. So this is the packed bed PBR. Now it is packed bed reactor, which consists of catalyst particle of vanadium pentoxide. Now here you can see the inlet temperature is 461, outlet temperature is 1115. So this is exothermic reaction. The benzene oxidation process is exothermic reaction. So the preparation of maleic anhydride by benzene process is the exothermic reaction. And remember, the partial oxidation of normal butane to produce the maleic anhydride is also exothermic process. So this is the exothermic process. Therefore, large amount of heat is released, and this heat is that heat increased the temperature of the product stream, which is stream number 6. So this stream will go to the cooler. We will decrease its temperature in order to increase our absorption process. So we will increase its temperature, decrease its temperature. So this is the cooler. This is cooler. And the inlet, what is inlet? Which component is in which stream is entering? Stream number 6. The product or the reactor product will entering. So stream number 6, and the stream number 7. This is stream number 7. Okay, require energy stream. So cooler energy. The cooler energy, unknown delta P. So we will go to the parameter. So in this the delta P in this cooler is suppose 10 kilopascal. Unknown duty. What is the duty of the cooler? So we want to decrease the temperature of this stream from 1115 to suppose 1115 to 60 degrees centigrade. Just assume 60 degrees centigrade. 60 degree centigrade. Okay. So here is the cooler duty. The cooler duty is 1.373 multiplied by 10 raised to the power 8 kilojoule per hour, and the delta T and pressure drop value is also calculated by the Aspen HYSYS. So this is the cooler energy. Okay. Now this stream will pass through the absorption column. This is the absorption column. So absorption column, and the stream number, this stream, now it is also quite heated, 60 degrees centigrade, so it will enter from the bottom of the absorption column, stream number 7, and from the top we will introduce from the top the absorbent or the solvent will use to remove the maleic anhydride from other dirty gases. So here absorption will taking place, and the absorbent or the solvent will be the dibutyl phthalate. So dibutyl phthalate will be used, and this is the top of the absorption column. So this is stream number 8. Suppose this is stream number 8. This is stream number 9. Stream number 9. Click on next. Now go to previous stage, and how many stages are in the absorption column? So I am assuming 12 number of stages. 12 number of stages. Click on next. The top pressure, what is the top pressure of the absorption column? So the top pressure of the absorption column is, suppose it is 82 kilopascal, and the bottom pressure of the absorption column is, suppose, 110 kilopascal. Now click on next. These are optional. So here it is unconverged, it shows unconverged. Click on run. So column feed, the error message, column feed stream dibutyl phthalate doesn't have enough information for the column to run. So we have not defined the dibutyl phthalate, we have not defined the absorbent. So we will define the absorbent, define this stream. So this is the temperature. Suppose the temperature of this stream is 30 degrees centigrade. 30 degrees centigrade. Remember, the dibutyl phthalate boiling point is 340 degrees centigrade. So this is in liquid phase and 30 degree. Okay, you can use 60 degree, 70 degree, 200, 100, etc. It depends on your problem. This is one atmospheric pressure. Suppose it is entering at 1 atmospheric pressure, and the molar flow rate of the dibutyl phthalate is, suppose it is 2400 kilogram mole per hour. Just assuming, I'm assuming these values. The dibutyl phthalate, this is the dibutyl phthalate. Pure dibutyl phthalate is used to absorb maleic anhydride from dirty gases. So click on OK. OK. Now the absorption column is specified. Now this is the distillation column. This is the distillation column. Double click on distillation column, and this is T101. This is distillation column. Distillation column. Distillation column. There are 10 number of stages, so I am just assuming 16 number of stages. Inlet stream. Which stream is entering to distillation column? Stream number 9 is entering to the distillation column. Stream number 9. Okay. And the inlet stage is stage number 8. The stream is entering to the distillation column at stage number 8. Okay. The condenser, that is, the condenser is partial condenser or total condenser. So I am using the partial condenser. This is a vent, and this is the top product or distillate. This is the top, and this is the reboiler duty. So this is QR, reboiler duty, condenser duty, QR. This is the bottom of distillation column. Now the numbering is from top to bottom or from bottom to top. So from top to bottom is okay. Click on next. Once through reboiler is okay, click on next. The condenser pressure. So what is the condenser? What are the condenser pressure? So I'm assuming 108 kilopascal for the condenser pressure, and the reboiler pressure is, usually the reboiler pressure is greater than the condenser pressure. So I will assume 112 kilopascal for the condenser pressure. This is the optional. Reflux ratio is, suppose, 2.3. Okay, done. Unconverged. It was unconverged. Click on run. So one or more specification are not fully specified. Click on OK. Click on OK. Now go to the monitor. This is active. Okay. This is, we have no information about distillate, so we will unactive. Deactivate this one. Deactivate this one. So we have some information about the vent. the vent molar flow rate and the top molar flow rate. So suppose the vent molar flow rate is vent rate and the top rate, the distillate rate. This is the distillate rate and this is the vent rate. Okay, so the vent rate is, suppose the vent rate is suppose 26 kilogram mole per hour, and the distillate rate is, suppose this is the distillate this connection. Okay, the distillate rate is supposed it is 30. Now activate this one, so it is converged, now close this one. This is converge, this is vent, top, bottom. Okay, this is top, bottom. So here you can see this is the now click on this stream number 6, that whether the reaction has taken place or not. So go to composition, and here you can see 1.42% maleic anhydride. Okay, now here go to the top and check the composition of maleic anhydride. So 98%, 98.27% maleic anhydride is produced in this case. You can use the shortcut distillation, but I am using the detailed distillation column. I have used the detailed distillation column. Go to the bottom, check the composition, 1%, 100% dibutyl phthalate. In order to increase the composition, the purity of the maleic anhydride. So this is the top product, and this is maleic anhydride. I will rename it maleic anhydride. In order to increase the composition of maleic anhydride to 99%. Or 99.2%, 99.3%, you can recycle this stream, this bottom stream, to the absorption column. The temperature here is quite large, 344 at the boiling point. It is at the wafer dibutyl phthalate. So we will decrease its temperature. We will place a cooler, and then we will add the recycle block, and the temperature will decrease to 30 degrees centigrade. The cooler will decrease the temperature to 30 degrees centigrade. The recycle, after cooling, we will put a recycle stream in order to recycle the stream. After recycling, this composition will be increased to 99%. You can also increase the composition by changing the benzene molar flow rate, the benzene temperature, the oxygen molar flow rate, the oxygen temperature. You can also check if you change the molar flow rate of air and natural gas, you can also increase or decrease the composition of maleic anhydride. So this was all about the manufacturing of maleic anhydride process, that how can we prepare maleic anhydride in industries using the packed bed reactor, distillation column, absorption column, fire heater, etc. So this was just introduction, that how can we prepare maleic anhydride. Thank you very much for your attention. In the coming lecture, we will use some optimization technique. We will use further designing of the maleic anhydride process. We will use the optimization process for the distillation and the absorber. Thank you very much for your attention. If you are new to the channel, please like and subscribe.